Hey, in this lecture, I'm going to go over what we traditionally do in class with the Nerf guns and or Nerf blasters and Adventure Force blasters with probability. So I'm going to go ahead and share my screen, and we will go through this. Hold on, stop sharing. Share. We want screen three. There we go. So in class Nerf worksheet activity. First, we are looking at Nerf blasters versus Adventure Force blasters. And in class, I have a lot of Nerf blasters, to be completely honest with you. I probably have upwards of 50. Why? I don't know. I just really like Black Friday and get them on good deals. And then I'm like, hey, I'll use them in class. And now I've gotten so many that I can't even bring them all to class. But so say in class, I bring in 17 Nerf blasters and eight Adventure Force blasters for a total of 25 blasters. And I let one student come up and choose their first blaster. And so this is what's referred to as prior probability. The question is what is it that they're going to choose? They have a 17 out of 25 chance or probability of choosing a Nerf blaster, and an 8 out of 25 is the probability of choosing an Adventure Force blaster. So, what's the probability of the first person will choose a blaster that's Adventure Force A or Nerf B? So, you notice probability of A is the probability of choosing an Adventure Force blaster, which, like I said, is 8 out of 25 or 32%. And you can see 8. So, the number of successes, what's considered a success here? A success is considered an Adventure Force blaster out of total number of trials, so 32%. So this is really important. A success is anything that you are measuring. So it's like, hey, what is the probability of this? Well, what's the probability of you getting shot with a Nerf blaster? Well, that would be whatever it is that's considered a success. Here, it's the success is whatever it is that you are looking for the probability of. Same thing here, probability of choosing a Nerf blaster. Here, the Nerf blaster is considered a success, the number of successes over the total number of trials. So 17 out of 25, so is a 68% chance of choosing a Nerf blaster. And this would be classical probability. Why is it classical? Because it's, once again, the number of successes divided by the total number of possible outcomes or trials. Okay, and also this is independent. So there is nothing that's impacting this individual's choice. Um, there's nothing that's affecting it besides that there's eight Adventure Force blasters and 17 Nerf blasters, and they get to choose. And so they've got a 68% chance of choosing one or a 32% chance of choosing the other. Next, so given that the first person chose an Adventure Force blaster, why? Because Adventure Force blasters, the ones that I have at least here, I've got some really junky ones, but I only brought the good ones. And so, needless to say, they're actually really decent. Adventure Force, what is it? It's kind of like, well, it's actually made by a company called Dart Zone. And I've got some that are made for Target, some that are made for Walmart. If they're made for Walmart, they're Adventure Force. If they're made for Target, I think they are labeled as Dart Zone. But the probability of A, probability of B. So given that the first person chose an Adventure Force blaster, what's the probability of the second person will choose an Adventure Force blaster or a Nerf blaster? So after the first individual chose an Adventure Force blaster, now everything changes. There's still 17 Nerf blasters, but there's only 7 Adventure Force blasters. So I've got the 24 remaining blasters laying on the ground, and the second person comes up and chooses the next blaster. Well, now the probability changes. What is the probability of the individual choosing a Nerf blaster? Well, there's only 24 blasters remaining because one of the Adventure Force blasters is gone. So, what is the probability of B2? So, B2 means the second person chose uh, the Nerf blaster, and then that line, that vertical line there, means given that. So what is the probability that the second person will choose a Nerf blaster given that the first person chose an Adventure Force blaster? And that is 17 out of 24. Why? Because there's 17 successes. 17 is the number of Nerf blasters that are left out of 24 possible blasters that they could choose from. So 17 successes out of 24 total possible choices. So that 17 divided by 24 is 0.71. So the probability that that student will choose a Nerf blaster is 0.71 compared to the previous one, which was 0.68. So the probability has gone up just slightly. Similarly, what is the probability that the second individual will choose an adventure force? Notice it says probability of A2 given that A1. So what's the probability of the second person will choose an adventure force blaster given that, that vertical line, given that the first person chose an adventure force blaster? Well, now there's only 7 adventure force blasters to choose from out of 24 total blasters. So this is 0.29 or 29% chance that the student will choose the Adventure Force Blaster compared to the previous one, which was 32%. So the probability that the second person chooses an Adventure Force Blaster, given that the first person chose an Adventure Force Blaster. And this is dependent or conditional probability. So it's dependent on the first person picking the Adventure Force Blaster. So the first one is prior probability. Then we've got conditional probability. Now we've got joint conditional probability. Whoa, joint conditional probability. That means that we're kind of bringing the two of them together. So what is joint conditional probability? It's when we have the probability of A1. So remember, what is A1? The probability that the first person will choose an Adventure Force blaster. What is the probability that the first person will choose an Adventure Force blaster and the probability that the second person will choose a Nerf blaster, given that the first person chose an Adventure Force blaster? That's how you read that probability of A1 multiplied by probability of B2, given that A1. So probability that the first person will choose an adventure force multiplied by the probability that the second person will choose a nerf, given that the first person chose an adventure force. Um, so just reading that all together, that's exactly what I just said. But you notice, the A1, I kind of show you choosing Adventure Force A1, and then the probability the second person choosing Nerf B2. So B2 is the two means second person. B is stands for that they're choosing Nerf, given that the first person chose Adventure Force. So this means the word and. Anytime that you see the word and, it means multiply. So probability of A1 is 0.32. Probability of B2 given A1, so probability of the second person choosing a Nerf given that the first person chose Adventure Force is 0.71. So what we need to do is we need to multiply the two of them. So probability that the first person chose Adventure Force is 0.32. Probability that the second person chose Nerf given that the first person chose Adventure Force was 0.71. So we just multiply the two of those together, and that gives us a joint probability, a joint conditional probability of 0.23. So that's the probability that the first person chooses Adventure Force, and given that the first person chose this is the probability that the first person chose Adventure Force and the second person chose Nerf, given that the first person chose Adventure Force. So that's how that works together. So that's joint conditional probability, and that's right at the top of your formula sheet. So I'm going to show you your formula sheet really quick. Let's see here. I'm going to pull this up. Dashboard. So let's go to your formula sheet. Unit 2. Uh, Printable resources. Unit 2 formula sheet. So notice right here, you've got prior probability, conditional probability, and then conditional joint probability or joint conditional probability, either one. And so you've got all three of those. This is what we just went through. And you notice we also have joint probability right down here as well, but we'll get into that in just a little bit. And now we are about to get into intersections and unions. And we also did classical probability. That's what we were doing, was classical probability just there. So let's come back here from current slide. So I had a big hula hoop, which I think, yep, I still have the hula hoop in my office. And so I held up the hula hoop, and I'll go grab the hula hoop real quick. I held up two different hula hoops. The first hula hoop that I held up, I let everyone shoot through, and there was a total of 32 people that shot darts. Of those 32 people, 21 of those individuals shot through the big hula hoop, and 11 did not. So using empirical probability, so first we were using classical probability because we were saying, oh, total number of successes out of total number of possible outcomes. Now we're saying, okay, based on our history, what is the probability of that essentially repeating itself? Based on the past data that we have, what's the probability of it happening again in the future? So if I were to have 32 people shoot again, the probability of would be, well, it wouldn't even need to be 32. It's saying, hey, why don't we have another person shoot? What's the probability that they will make it through the hula hoop? Well, it's 65%. The probability that they will not make it through the hula hoop, which is 35%. And how did we calculate that? Well, 21 people made it through the hula hoop out of 32. So 21 divided by 32 is 65%. Past successes divided by number of trials. And then there was 11 people who did not make it through the hula hoop. So that's 11 out of 32 or 35%. Once again, past successes divided by number of trials. And so then we did, so that was an experiment. Well, technically it was 32 experiments. Um, and then we have two possible outcomes. They made it through the hula hoop or they did not. And then the collection of all of that, the event is 21 people made it through the hula hoop, 11 did not. Then we did it again, except this time we had a smaller hula hoop. So the big hula hoop, the small hula hoop, and here we go. The total number of darts shot. Somehow there were 33 darts shot this time. I guess more people just wanted to shoot. So how many students made it through the little hula hoop? This time, 16 people made it through the little hula hoop, and 17 people did not make it through the hula hoop. And so when we calculate for empirical probability, 16 successes out of 33 trials is 0.48 or 48% made it through the little hula hoop. And then if we are considering, how many students did not make it through the little hula hoop as, the successes. So 17 out of 33, once again, number of successes divided by number of trials, is the empirical probability of an individual not making it through the hula hoop. So that's 52% is your probability, or 0.52 is your probability of not making it through the little hula hoop. And so we're just calculating the empirical probability there. And then I did something silly because I stood up in the front of class and I held up both hula hoops. And I held them up separately like this. And there's a total of 3 possible outcomes. They either made it through the small hula hoop, they made it through the big hula hoop, or they did not make it through any hula hoop, which normally ended up with them hitting me in the middle. So yeah, there were a total of 12 out of 30 people who made it through the big hula hoop. There were a total of 10 out of 30 people who made it through the little hula hoop. And there were a total of 8 out of 30 people that did not make it through either. And a lot of them hit me. So what was the probability? If I have all 3 of these up, first of all, these were all mutually exclusive. You could not make it through the big hoop and the little hoop because they were separated. So when they are mutually exclusive, there was a 40% chance of making it through the big hula hoop based on, once again, empirical data. There is a 33.3% chance of making it through the little hula hoop because 10 out of 30 made it through. And then 8 out of 30 is 0.2667 or 26.67% chance of missing. And so these are all mutually exclusive, which is very important. And the reason why is we can determine what is the probability of what is the probability of an individual making it through hoop A or through hoop B when they are mutually exclusive. And the reason why this is really important is when they are mutually exclusive, you can literally just add them up together. And there's a this little U right here means union, which means or. And when you see the union or, it means add. You need to add the probabilities together. So what's the probability of making it through the big hula hoop? We determined it was 12 out of 30 or 0.4. What's the probability of making it through the little hula hoop, which is 10 out of 30 or 0.333? So you take the probability of A plus the probability of B, so zero point 0.4 plus 0.333, and that gives you 0.733, which I just realized there is no point right there. So 0.7333 or 73.33%. So once again, the probability of making it through the big hula hoop plus the probability of making it through the little hula hoop, you can just add those probabilities together to say what's the probability of you making it through the big hula hoop or the little hula hoop. And the reason why you can just add those together is because they're mutually exclusive. But if they're not mutually exclusive, we need to do it a little bit different. Remember the very first shot that the students took, they were shooting at the big hula hoop, and 21 out of 32 students made it through the big hula hoop. And then the second shot that they took, it was 16 out of 33 students made it through the little hula hoop. So that's 48.48%, and then also 65.6%. And so, yeah. Uh, so with the first shot at the large hula hoop and the second shot at the small hula hoop, what's the probability of making it through the large hula hoop or the small hula hoop? So what we're saying is when we look at those first two shots, remember the very first shot that everyone took, they took a shot at the big hula hoop. And then they got another shot. They shot at the little hula hoop, which now they are no longer mutually exclusive. You can make it through the big hula hoop, and then you get a second shot. That same person can also make it through the little hula hoop. So we can't use the same rule, the same way that we calculated the probability of A and B. We can't do that anymore. We've got to do it slightly differently. So we are going to use this formula right here. It says the probability, when it's not mutually exclusive, we do the probability of A plus the probability of B minus the probability of A and B. And I'm going to once again show you the formula sheet because it is right here, the union, rule of addition. Probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And so let's look at this. Let's current slide. So when you see more of like an N looking thing instead of the U, that means and. And so we've got the probability of A and B. Sorry, the probability of A plus the probability of B minus the probability of A and B. Now, why is it that we need to subtract the probability of A and B? That's a great question. So, first of all, when we add up the probability of A and B, what does that calculate to? Let's take a look for a second. Okay, so, oh, we already did it. Probability of A plus the probability of B, so that's 65.6% plus 48.48%, and that gives us 114%. First of all, there is no way that you could ever have 114% chance of making it through hoop A or B, or making it through the big hoop or the small hoop. It's not possible. You cannot get above 100%. The reason why it's above 100% is when you are calculating the probability of making it through the big hoop, and the probability of making it through the little hula hoop, it is counting this middle section twice. So it's like, hey, I'm going to calculate the probability of making it through the big hula hoop, which is 0.656. I'm going to calculate the probability of making it through the little hula hoop, which is 0.484. 4848. Okay. Um, and so you add those together, and there's this overlap area where it's being counted twice. It counts it once as part of a big circle, once as part of the little circle, but you only should count it once. So we need to subtract it once so that way it's not counted twice. So we do the probability of A plus the probability of B minus the joint probability of being in this middle section of A and B. So 32% of individuals made it through both. And the way that we got that, okay, uh, this little n right here means and, which means multiply. Okay, so how are we going to do this? What is the probability of making it the first and second? So this is the joint probability. In order to do this, probability of A multiplied by the probability of B. So it's 0.656 multiplied by 4.484, which gives you 0.32 or 32%. Okay. Um, Well, let's do that. 0.32 or 32%. So roughly 32% of individuals make it through both. So what we're going to do now is put it all in one big long formula together. 0.656 plus 0.484 minus 0.32 equals 82.4% or 0.824. Let's do 4, 82.4% of individuals made it through through the big hoop or the little hoop. So 0.824 is the probability of making it through the large or small hoop or both. So it doesn't matter if you make it through just the first one, if you make it through just the small one, or if you make it through both of them, you're counted as part of that 82.4%. And then we can use the complement rule. What's the probability that you don't make it through either? So if you do 1 minus 0.824, that will give you the probability of not making it through either, which is going to be roughly 17 point or 0.176 or 17.6%. And you can see that once again on the formula sheet, the complement rule, the probability of not making it through this is 1 minus the probability of making it. So that's the complement rule that we will use a lot. So make sure that you're constantly referring back to this. The more that you refer back to this, the better you're going to do. So please keep referring back to this throughout this entire unit. So we've got the joint probability. We've got shot one, shot two. What's the probability of making it through the hula hoop in shot one, through the big hula hoop or the little hula hoop? And that is going to be 82.4% because we did probability of A plus the probability of B minus the probability of A and B because we didn't want to count this twice. And so that's how we do this with both hula hoops and with joint probability and conditional probability. Hopefully, going through this was beneficial. And yeah,